Hi everyone, this is Vishwa from IIT Roorkee. I'm going to explain about relationship between Laplace and Fourier transform. These are my agendas. Introduction to transforms, Laplace transform overview, Fourier transform overview, historical context, fundamental differences, mathematical foundations, relationship between Laplace and Fourier transform, application in engineering, case studies, future trend, and conclusion. Introduction to transforms. Definition of transforms. Transforms convert signals between different domains and facilitates analysis. Role in signal processing. Transforms are fundamental in solving engineering problems related to signal analysis. Laplace transform overview. The Laplace transform analysis linear time invariant system in S domain. Fourier transform overview. The Fourier transform focuses on frequency components, converting time signals to frequency domain. Common applications. Both transforms are widely used in control systems, communications, and circuit analysis. Key differences. Laplace transform handles stability and transient behavior. Fourier is for steady state analysis. Interrelationship. Fourier transform is a special case of Laplace transform when the imaginary axis is considered. Laplace transform overview. The definition of Laplace transform transforms a time domain function into complex frequency domain, aiding analysis. Application in linear systems used to analyze linear time invariant systems, offering solutions to complex problems. Differential equations facilitates solving differential equations by transforming them into algebraic equations. Comparison with Fourier transform. Both transforms convert functions, but Laplace handles exponential growth effectively. Region of convergence. The Laplace transform includes a region of convergence that defines stability conditions. Inverse transform. The inverse Laplace transform reverts functions back to time domain for analysis. Fourier transform overview. Decomposition of functions. Fourier transform separates a function into its fundamental frequency components, enhancing analysis. Signal processing application. In signal processing, the Fourier transform is used to analyze frequency content in signals, aiding in noise reduction. Physics relevance. In physics, this transformation helps in solving problems involving wave functions and vibrations. Engineering utility. Engineers utilize the Fourier transform to design systems that respond to specific frequency inputs. Foundation for Laplace transform. The Fourier transform serves as a basis for Laplace transform, linking time and frequency domain. Historical context. Introduction of Fourier series. Jean-Baptiste Joseph Fourier introduced the Fourier series, establishing a crucial foundation for Fourier analysis, which allows for representation of periodic functions. Development of Laplace transform. The Laplace transform was developed in 19th century to manage more complex systems in engineering, providing tools for analyzing linear time invariant systems. Fundamental differences between Fourier transform and Laplace transform. Fourier transform focuses primarily on frequency components of signals, ideal for analyzing periodic signals in time domain, utilizing trigonometric series for representation, widely used in signal processing and communication, transforms a time domain signal into frequency domain, helps in identifying harmonic and spectral content, applicable mainly for steady state analysis, enables reconstruction of signals from frequency data, less effective for transient behavior analysis, requires periodical for accurate representation, output real and imaginary parts of frequency components, commonly used in audio and image processing, facilitates filtering and modulation techniques related to concept of Fourier series for periodic functions, easier to compute for simple periodic signals, Laplace transform, incorporates complex frequency for analysis, suitable for transient state analysis in signals, employs complex functions for representation, widely used in control systems and differential equations, transforms time domain signals into complex frequency domain, enables analysis of system stability and behavior, applicable for both steady state and transient analysis, facilitates the solution of ordinary differential equations, more robust for initial conditions and non-periodic signals, outputs a complex function of complex variable, commonly used in electrical engineering and physics, helps in system design and analysis, can handle a wider range of functions and signals related to concepts of inverse Laplace transform, easier to compute for complex and non-periodic signals. Mathematical foundations. Here is the equation for Laplace transform and Fourier transform. Application of Laplace transforms used for system dynamics and control theory. Applications of Fourier transform used for signal processing and frequency analysis. Relationship between transforms. Laplace transform, a mathematical technique that transforms a function of time into function of complex frequency. Fourier transform, a method that decomposes a function into its constituent frequency, widely used in signal processing. Generalization. Laplace transform serves as a broader framework that encompasses the Fourier transform within its scope. Problem solving. Leveraging both transforms enhances analytical capabilities in engineering and physics applications. Applications used in control systems, differential equations, and signal processing to simplify complex problems. Relationship between transforms. Fourier transform of continuous time signal xt is defined as x omega is equal to integral infinity to minus infinity xt e to the power minus j omega t dt. And then like we include inverse Fourier transform. Now we are replacing omega by sigma plus j omega. This will change the inverse Fourier transform into xt is equal to 1 by 2 pi integral infinity to minus infinity x sigma plus j omega e to the power sigma plus j omega t d omega. Now substituting the values from fifth equation and sixth equation, we get the final equation, the relationship between Laplace transform and then Fourier transform. Lxt is equal to fxt e to the power minus sigma t. Applications in engineering. Laplace transform in circuit analysis. Crucial for analyzing electric circuits, enabling the solution of differential equations, control system and applications. Used extensively for system stability and control design through system modeling. Communication engineering facilitates the analysis of signal behavior, improving the communication system and designs. Fourier transform in signal processing, essential for analyzing and processing digital signals, optimizing data transmission. Image analysis application, utilized in image processing to enhance and extract features from images. Case studies. Laplace transform in AI and automation enhances the system analysis capabilities. The Laplace transform is a pivotal in analyzing dynamic systems, essentially in AI, where it streamlines the evaluation of complex behaviors. Fourier transform in digital image processing. Advancements in Fourier phase only synthesis. Fourier transform plays a critical role in digital image processing, enhancing the image quality through advanced phase synthesis techniques. Future trend Laplace. It's used in AI multidimensional analysis. For Fourier transform, it's used in phase synthesis techniques. Conclusion The exploring synergy between Laplace and Fourier transform enhances problem solving in engineering. Thank you.